This is an experiment. This is the first video I've done of this type, dealing with answering questions that are on the homework. So this is for conceptual physics. This is the chapter 2, think and solve problems. Now the essence of these 4 problems that are assigned are the forces up equal to forces down. In general, when you're talking about equilibrium, that the total force equals 0, and because forces are vectors, direction matters. And so in these 3 problems, we're only dealing with forces up and down. We can get into some subtleties here and some other things that really are beyond what we need to talk about in chapter 2. And we might in class, but as far as the homework is concerned, just forces up equal to forces down. So we start out with Lucy Lightfoot stands with 1 foot on one bathroom scale and her other foot on a second bathroom scale. Each scale reads 350 newtons. What is Lucy's weight? So problem 27. So if the scales are reading each 350 newtons, that is the force that she is pushing down on the scale. Now, if she's pushing 350 newtons down on the scale, that means there's 350 newtons pushing up on her. And if we assume that she is in equilibrium, we assume she is not bouncing on the scales, because that changes the problem. If any of you have ever bounced on an analog scale, you know that the dial will flip back and forth. But if she's just standing there, not bouncing at all, then the force is up on her, which would be 700 newtons, it's 350 from each scale, equals to the force acting down. And so, therefore, that force acting down on her is 700 newtons, because there's 700 newtons up, 700 newtons down. To put her, the total force acting on her is 0, because the forces up, forces down will neutralize each other. So the force down is her weight. That's 700 newtons. Now problem 28. Henry Heavyweight weighs 1,200 newtons and stands on a pair of bathroom scales so that each scale reads twice as much. So one bathroom scale reads twice as much as the other. What are the scale readings? Well, I know that the total force up has to be 1,200 newtons. Now there are some algebra ways of going about that, but just sort of jumping over that. If one measures twice what the other one does, then whatever they add up to, it has to add up to 1,200. So 800 and 400 would work. 800 is twice 400, and the sum is 1,200. From an algebra point of view, if you think about one scale measures x amount, let x be the variable. The other one measures 2x. So x plus 2x equals 1,200. 3x equals 1,200. X equals 400. So if one scale is 400 newtons, the other scale is 800 newtons. In 29, the sketch shows a painter's scaffold in mechanical equilibrium. The person in the middle weighs 500 newtons, and the tension in each rope are 400 newtons. What's the weight of the scaffold? Again, the forces up equal the forces down. We have 800 newtons pulling up. So therefore, if it's in equilibrium, as the problem does state this time, then there's 800 newtons pulling down. Well, 500 of that is him, and so the scaffold must be what's remaining. So if I have 800 up, and I know 500 is acting down, well, there's a missing 300. That's the scaffold. The weight of the scaffold has to be 300 newtons. In problem 30, a different scaffold that weighs 400 newtons supports 2 painters, one 500 newtons, the other 400 newtons. The reading in the left scale is 800 newtons. What's the reading in the right-hand scale? So again, forces up equal forces down. The difference between this and the previous problem is this time we know all the forces down. We have to figure out the total force up, or the missing part going up. So the total force down is 1,300 newtons. That's 500 plus 400 plus 400. I'm assuming you're looking at the book when going through this. So there's 1,300 newtons down, so there must be 1,300 newtons going up. I know what 800 of that is, so there's a missing 500 going up. So therefore the force upwards on the right-hand side must be 500 newtons, because 500 plus 800 equals, that's the force up, equals the total force down, which is 500 plus 400 plus 400 newtons. And again, just a couple other notes here. Newton is the unit of force. It is what's considered the SI, the Standard International Unit of Force. And so that's why they keep using newtons there.